So again, same lesson, proportional linear relationships, 12, 9, 15. Two quantities that have a constant ratio and a constant rate of change. That's a proportional linear relationship. So what are some things that we need? First, you must have several ordered pairs okay? And these ordered pairs are going to be, we must be describing two different values. So what I mean by values, it's not numerical, it's like types. So for example, the last one was cups of vinegar versus cups of oil. So they weren't the same thing. It wasn't vinegar and vinegar or oil and oil. It was two different types of values. So we must be describing two different values, and we must have several ordered pairs. Oops. Sorry. And then we must calculate using division each ratio. Okay. So what we're going to come up with is two possible outcomes. Ratios are equal, then that's called proportional. The other option would be ratios are not equal, so that's not proportional. Okay, so what you're going to be given is a chart, and out of that chart you're going to create ordered pairs, and from those ordered pairs you're going to be able to calculate ratios. We also are going to do what we did yesterday to test to see if it's linear. So we are going to look at, is there a constant value that one item changes by? Is there a constant value that the other item changes by? If the answer is yes and yes for both of those, then it's linear, okay? Okay, so let me give you some information. This comes about temperature for two different systems. Our system and everybody else's system. So we use Fahrenheit and the rest of the world uses Celsius. So we have degrees Celsius. So degrees is that little circle that we use next to our numbers in temperature. So Celsius, oops, I did that again. It's an S. And we're going to compare it to degrees Fahrenheit. Okay, and we've got, when it's 0 in Celsius, it's 32 in Fahrenheit. When it is 5 in Celsius, it's 41 in Fahrenheit. When it's 10 in Celsius, it's 50 in Fahrenheit. And when it is 15 in Celsius, it's 59 in Fahrenheit. And last, when it's 20 in Celsius, it's 68 degrees in Fahrenheit. Now, the reason why the rest of the world uses the Celsius system, the metric system, versus Fahrenheit, traditional system, is because it's actually easier to calculate with. We have freezing. In our temperature is 32, but in Celsius it's 0. Boiling for us is something like, I don't know, 212, something like that. And in the Celsius it's 100. So these are a lot easier numbers. So all scientists use Celsius because of it being an easier problem to deal with. All right, so let's check to see if it's linear. To do that, we just look at differences. So to get from 0 to 5, we added 5. To get from 5 to 10, we added 5. To get from 10 to 15, we added 5. To get from 15 to 20, we added 5. So that checks out as being the same. And then we're going to check the Fahrenheit. To get from 32 to 41, let's see, I added 9. And from 41 to 50, I added 9. And from 50 to 59, I added 9. And from 59 to 68, I added 9. So that checks out. So what this tells me is that there is a linear relationship. If there's a linear relationship, then that means I can calculate the constant rate of change. And again, remember that degrees Celsius is your X and degrees Fahrenheit is your Y. And it's all dependent upon placement. So whatever's on top is your X and whatever's on the bottom is your Y. When I'm doing the constant rate of change, I'm just going to take the change in the Y over the change in the, X. So for us, what was the change in the Fahrenheit every time? 9. What was the change in the Celsius every time? 5. So that's our constant rate of change, is 9 over 5, or 9/5. So now what we want to check, is it proportional? Oops. So to do that, we're going to have to compare each of our ordered pairs in that Y to X fashion. So we're still going to use this, but not over the change, over the individual. Now, there's one combination that we can't check. This one. Why can I not check to find the ratio of 32 to 0? Sean? It is a number, but there's a reason why. And it does have to do with 0.
32 can't go into 0?
Actually, it can, but that's not the way this problem is written. Joy? Actually, it doesn't equal 0. Cameron? It doesn't equal 32. Breck? Actually, the denominator is in charge of telling you how many groups you can break it into. Okay? So 32 divided by 0 is impossible because we cannot take 32 and break it into nothing, into groups of nothing. It's impossible for us to do this. This prevents us from having to solve this problem. You can't divide by 0. So we're going to ignore any time we have a ratio where 0's in the denominator, we're going to ignore it. Because it's just something mathematically I can't do. So I'm going to look at my other ratios and see if I can find something. So I had 41/5. So I'm going to change this into something that makes a little bit more sense to me. And see, 5 goes into 48 times, and there's 1/5 left over. Okay, so I just did a little division and came up with a mixed number. So that's what I'm looking for. If this is a proportional relationship, every time I take my ordered pairs and divide them, I should get 8 1/5. Okay, so we'll try the next one. 50 divided by 10 equals 5. So right now is when I stop and I say, since 8 1/2 does not equal 5, this is not proportional. Okay? So that's what we're looking. We're looking at two different groups of data in order to determine if we have something that's proportional versus something that's linear. Linear is looking at the change in my x values to see if that change is always the same, and the change in the y values to see if the change is always the same. If the change in x is the same and the change in y is the same, then we have a linear relationship, and we can figure out that constant rate of change. But to do the proportional, we take each individual ordered pair and do division with them, y divided by x, and see if the quotients we get match. If they don't, it's not proportional. So this one is linear, but it's not proportional. Okay? So if I graphed it, I would get a line. It would look like it would be a line. Sean?
For the, like 41 and 5, and like the 50 and 10,
Uh-huh.
you just
I just start it, here's my rule of thumb. I just start at the beginning, and if, like I said in this one, I had one that was dividing by 0, which mathematically we can't do, so I skipped over that as a possibility. So I did the next one, 41 fifths. And then I did 50 tenths. If 50 tenths had the same quotient as 41 fifths, I would do 59 fifteenths. If that was the same, then I would try 68 twentieths. But as soon as I see a difference, I don't need to do anymore, because I already know it's not proportional, because I had already 2 of them that didn't match up. So as long as, if I can find 2 that don't match, I'm done. Okay, so I just start and I just go systematically from the beginning of the chart to the end of the chart. So let's do another one, but this time it's gonna be one that's proportional, so you can see how that looks. All right, so this problem, and I'm gonna write it differently. This is looking at weight in pounds versus mass in kilograms. So our weight in pounds is going to come first, and our mass in kilograms is going to come second. So remember, when we write our chart vertically, X, Y, it's that alphabetical order, right? So let's see what our pair up is. When I have a weight of 20, it has a mass of 9. When I have a weight of 40, it has a mass of 18. When I have a weight of 60, it has a mass of 27. And when I have a weight of 80, it has a mass of 36. So first thing I'm going to do is check to see if I have a linear relationship. So I'm going to look for the change in my x values. So to get from 20 to 40, I would need to add 20. To get from 40 to 60, I would need to add 20. To get from 60 to 80, I would need to add 20. So this one checks out as being a constant change. Okay? Help me out on this one. What do I do to get from 9 to 18?
9.
So I add. It gets bigger.
I know, but to find it,
No.
subtract 18 and 9.
That's right, but find is tell me the answer. And I wouldn't have a minus sign, I'd have a plus sign because I'm increasing. Okay, and then to get from 18 to 27, I get positive 9 again because it's getting bigger. And what about 27 to 36? Okay, so this also is constant. Okay, so let's try this again. So because these are constant, this means we have a linear relationship. This is linear. Oops. And because it's a linear relationship, we can figure out the constant rate of change. Rat. And what I do is, again, for the constant rate of change, is have the change in y over the change in x. So for us, the change in y was 9, and the change in x was 20. And so we get 9/20. Okay? Now, let's check to see if it's proportional. We still use the idea of y over x, but we're going to look at it ordered pair to ordered pair. Okay? So we have 9 over 20 for our first ordered pair. Well, I can't simplify that, so that works. So now I'm going to try 18/40. So let's see, they're both even, so I divide by 2 and I get 9/20. Ooh, this is good. So far I've got a match. Both say 9/20. Got to keep testing. I got to go through all 4 of them before I can say yes. So let's see, these guys have, what, a 3 in common? So this one I divided by 2. This one, if I divide by 3, I get 9/20. This is looking positive. And then I still have to test one more. 36 over 80. So let's see, these guys have a 4 in common. And that gives me 9 over 20.
So you divide like every single one?
I take my each ordered pair and I create a ratio, a fraction, and I simplify it. And I don't have to go to decimals. I can just simplify it down to a fraction. So what we notice is every single time the ratio of mass to weight always came back to 9/20. So we have, yes, it's proportional. So we end up having a proportional relationship. So we get both. Okay. So hopefully, Sean, that answers your question is how far do I go? I go to the end. Okay. If I find they don't match early on, I stop. Because I don't need to do any more. I've already proved that they aren't proportional. Okay. All right, Talia.
So if it's not proportional, I mean like if there's like no constant rate of change, it's not proportional, right?
Well, you could have proportional without linear. It is possible to have one without the other. We've had linear without proportional, right? So that is something that you just mathematically test out. Okay? So our constant rate of change, and by the way, we could write it this way, is that there's 9/20 of a kilogram per 1 pound. Now, when you get into your science classes, you're going to, in high school, you're going to learn the conversion a different way, and you're going to learn what 1 kilogram is, because it's an easier way of doing it, and it equals approximately 2.2 pounds. So you're going to be doing conversions between pounds and kilograms when you're in your science classes in high school. Okay?